Good morning, everyone. I'm really excited this morning to introduce our 12th CCC speaker today, Dr. Gabriela Gomes. Dr. Gomes is a professor of mathematics and statistics at the University of Strathclyde, Glasgow. She's an expert on nonlinear dynamics and mathematical modeling of infectious diseases, and her research has spanned a number of diseases and topics. And really, she's a leader in bridging evolutionary biology and thinking with epidemiology to bring novel perspectives to disease systems. Specifically, she's worked on a number of important disease dynamics when thinking about disease dynamics when immune protection from the disease is imperfect or waning. In such cases of that are in pertussis, tuberculosis, and influenza. And then also she's done a number of important papers on the dynamics of seasonal diseases. Recently, her focus has been primarily on how population heterogeneity alters disease dynamics, specifically how it can almost always reverse the direction of previous conclusions when properly accounted for. And she's presented frameworks for thinking about paths to eliminate tuberculosis, how mosquito competence heterogeneity to Wolbachia can alter Zika and dengue dynamics. And most recently, she's been thinking a lot about how population heterogeneity in susceptibility and transmissibility to COVID-19 can impact the herd immunity thresholds, which I think is what she'll be discussing today. So with that, I'll let her take it away.
Okay, yeah, thank you. That's a very nice introduction, Spencer, and thank you, Lauren, for inviting me, and Spencer for inviting me to speak at your consortium. So, yeah, I've known of course of you and your group for a long time. We have never actually met in person, but I know people who have worked with you, and I know of your work on contact networks. That's really important, and in a way, not far from the ideas I'll be presenting here. So I hope there'll be some nice synergy coming out of these, and we'll find some nice overlap and common grounds for maybe future collaborations, who knows. So I'm going to try to share my screen. So I guess I'll just go like that, share and make this big. Is this okay? You see my slides?
Yeah, perfect.
Okay. Yep. So I'll be mostly focusing on this preprint, which has been on medRxiv for 2 or 3 weeks now, and this is in collaboration mostly with actually Brazilian and Portuguese authors. So when this pandemic started, I was moving between institutions, and this is actually a very informal group. It's not a formal team. Names you see here do not. You see, each one comes basically from a different institution. So what happened is that when the pandemic started, I was moving between the Liverpool School of Tropical Medicine, where I worked before, to the University of Strathclyde, to a mathematics and statistics department, and then they said, well, everybody will work from home. So everybody will work from home. I didn't have a home in the UK, so I came home to Portugal. So I'm actually sitting here in Portugal near my family, my extended family, and I had these ideas. I just felt that models that I was reading, so this was about early March, mid-March, the models I was reading just didn't seem to be accounting for individual variation in susceptibility and exposure to infection in the way that I felt that should be accounted for. So I based on work I had done for other diseases. So I just started developing some models, but then very quickly it just became overwhelming for just a single person to look at the data and do the models and think about the theory. So I got in touch with former students mainly, and former collaborators that I had worked on other diseases. So that's how this team was assembled, and I even I even brought my daughter into this. So Jessica King is my daughter. She's doing a PhD at the University of Edinburgh in evolutionary biology, and she actually became part of this effort. So it's a very informal team, and I think I'm stressing this because in a way it was very exciting to get these people working together on this, but on the other hand, we feel we don't really have quite the capacity and the organization to do this at the same scale that bigger groups are working. So it's a bit frustrating. Yeah, we just feel that there's so much to do, and there's so many other contexts where you could apply these ideas, and we feel limited in terms of sort of human resources at the moment. So that said, I'll tell you why I thought that individual variation was so important to consider here. So we consider a sketch. So it's just a sketch for intuition, like I present for general talks to general audiences. Maybe this wouldn't be needed here, but just as well it goes. So let's consider individuals. If we consider the individuals in a population, in a homogeneous population, they all have the same susceptibility and exposure. So when infection comes, so a virus invades this population and is going to infect individuals at random, it doesn't really matter which individual is infected in terms of building immunity. So the way I'm sketching this here is that immunity, when an individual becomes immune, their susceptibility moves from this baseline level to the bottom or close to zero. It doesn't have to be exactly zero, and it just paints this green area, and this green area is immunity, is the population immunity. So and somehow when this population immunity reaches a threshold, then you prevent future epidemic growth for this virus. So that's the herd immunity threshold for a homogeneous population. So what would happen if you have a heterogeneous population, if individuals vary in either susceptibility or exposure to infection? Now, here you are ordering the individuals by susceptibility times exposure. And when the virus comes, the individuals that are more likely to be infected are the individuals that either have higher susceptibility or higher exposure. They have a higher product susceptibility times exposure. And if this population has the same average susceptibility times exposure as the homogeneous population, then you need less individuals to paint the same area of immunity. So this immediately tells you that the herd immunity threshold is lower for a heterogeneous population than for a homogeneous population. So conceptually, I think it makes a lot of sense. It's hard to imagine how this could be any different from these conceptually. So the question is, how much? What's the size of this effect? How different is this percentage of individuals that need to be immune in comparison with the percentage of individuals that need to be immune according to the homogeneous model? So in order to analyze that, so we built a model where we introduced a continuous distribution of susceptibility into what otherwise would be an SCIR model. So here are the equations. We just have a standard SCIR model, and now there is this variable x. So for each level x, for each level of susceptibility x, we have, we want to track the susceptibles, exposed, and infected. The remaining are the immune individuals for each level of susceptibility x. So this is a continuous distribution. In theory, in practice, we have discretized it into many susceptibility bins, something like thousands of susceptibility bins. So it's actually an approximation of a continuous distribution. And and this is the force of infection. So of course, an individual in in a particular susceptibility group, so susceptibility goes here, multiplying the susceptibility for each group by factor X. So an individual in a particular susceptibility group can be infected by an individual of any other susceptibility. So the force of infection is this integral over all susceptibility group levels. And so we applied this model to so epidemic curves. So we fitted this model to epidemic curves from several countries. In the paper we decided to focus on 4 European countries. And this is what we estimate. So we have the fit, so these orange curves are the fit of these outputs of this model, fits of this model to the daily new cases in each country. And we estimated the parameters. So we assumed that distribution was a gamma distribution with mean 1 and some coefficient of variation that we treated as a parameter that was going to be estimated. And we estimated R0 and C and the coefficient of variation for each country. We assumed these other parameters, delta, gamma, and rho, so the rates of transition from exposed to infection and recovery from infection, and relative infectiousness of exposed in comparison with the fully infectious individuals. We consider these parameters in agreement with what we saw in the literature, because we couldn't really estimate everything, but we estimated R0 and CV for each country. And then having the coefficient of variation and R0, we could then actually see when the herd immunity threshold was expected to be crossed, and this is the vertical line. So we simulated these, and we can see that for each country we also implemented social distancing, and we assumed a certain profile for the social distancing. So it started to take effect gradually, and then it reached, for about a month, it reached the maximum effect. And this is when when countries were implementing the full lockdown, and then lockdown was relaxed, and the contacts started increasing gradually again. Eventually it will go back to a normal level, but it's just, we don't know when that will be. And of course, these projections depend on what we assume about this return to normal contacts. But for the purpose of estimation, we only applied this profile of social distancing for the duration of time where we have data, which is until July or so, until through the first week of July or so, when these fittings were done. And then after having completed these fittings, we found this data on mobility data from Google, and we just show it here on top of these plots. These data were not used at all in our fittings, in our estimations. We just show it here just to show that it's kind of consistent with the estimates we are making. So we gave our model no information. We gave our fitting no information whatsoever about when social distancing started and what the maximum effect was going to be. This was just estimated. We gave it a shape. We just say, well, let's say that social distancing increases linearly for 3 weeks, and then it stays at maximum for 1 month, and then it is relaxed over a period. We did some sensitivity analysis. It could be relaxed over a period of 4 months, 5 months or 6 months, and the results really don't change very much if we make this if we make this return period vary within this range. And so we and the herd immunity, and so what's the herd immunity threshold we obtained for these different countries? So we estimated herd immunity threshold given all these parameters having been estimated. We could then calculate what was the corresponding herd immunity threshold, and that turned out to be almost 10 for Belgium, and 20 for England, 12 for Spain, and a bit less for Portugal, a bit lower than 10 for Portugal, about 7 in this heterogeneous susceptibility case. So when we look now at the herd immunity thresholds over a range of coefficients of variation, we actually have a formula. This formula was developed by our collaborator Antonio Montalban. He is not on this paper, but we have another paper where he develops the mathematics. So he's at the Department of Mathematics at the University of Berkeley, and we have a separate preprint where he actually derives these formulas for the herd immunity threshold, including these coefficients of variation in it. So now we have a coefficient of variation over a range, and we have the herd immunity threshold according to this formula. And when we make coefficient of variation equal to 0, then we get these classical herd immunity thresholds of higher than 60% for the values of R0 that have been estimated for COVID, about 2 point something or higher. And but now we have this the coefficient of variation, and we see that the herd immunity thresholds really drop very sharply as soon as the coefficient of variation starts to increase. And here we have for England is this magenta color. It's when we estimated R0 to be lower, and given the coefficient of variation we estimated for England, we estimate herd immunity threshold. So we calculate the herd immunity threshold just over 20%, and that's showing here. And the dashed lines are the corresponding epidemic final sizes. So the attack rates if the epidemic had been left unmitigated. So the difference between the herd immunity threshold, the full line, and the dashed line is what some people are calling the epidemic overshoot. So if we had left the epidemic unmitigated, we would have seen almost 40% of infection, 30-something percent of infection, but mitigation, so social distancing and lockdowns, and so can keep these overshoots under control. And so ideally we would have an epidemic final size that would be as close as possible to the actual herd immunity threshold. So that would be the perfect mitigation, I guess. Yeah, and herd immunity would eventually be achieved when you had reached the herd immunity threshold. So this is variation in susceptibility. We also looked at regions. When we look at regions within a country, we see that the differences can get bigger, so we can get a wider range of herd immunity thresholds, but already, it's clear, as expected, a herd immunity threshold is not the same for every country, but even within a country, it's not the same for every region. So this is Spain. We did this for Spain because when we were doing this, there was a serological survey from Spain that had just been published, and it had very good comments. We saw very good comments about the way it had been done. It was a large study covering the entire country, and it's really randomized. So it seemed to be So we decided to focus on Spain for the comparison of our prevalence, according to the prevalence, the cumulative prevalence according to our model, to compare that with seroprevalence according to a serological survey. So then the results are here on the right. So for Spain, here we are considering the Madrid region, which was a region that was affected earlier and most strongly in this pandemic. And then there's a Catalonia region where Barcelona and other cities are, and it was more moderately affected. And then the rest of Spain, which has collapsed the rest of the country in one patch for this. For this analysis, and these segments, they are the confidence intervals that came from serological studies. So consistently, we see that the serological studies, the seroprevalence according to serological studies is consistently lower than cumulative prevalence according to our model, which seems to agree with also other studies that are being saying that the antibodies wane, so you don't find antibodies forever when after a person has been exposed. And it's actually been found even actually from the Spanish study that they did a longitudinal study, and they see that some individuals that had antibodies earlier on, a month or two later, they no longer have those antibodies. So we think that's why these seroprevalences are lower than our cumulative prevalences, but it was just, we thought it was interesting to show this comparison. And here we see that in Madrid, we see the herd immunity threshold of 20%, even though we had estimated the herd immunity threshold for the entire country to be 12%. So there's going to be this variability when we say that herd immunity threshold is being achieved. I think it's not saying, hey, stop worrying, let's everybody can relax and go back to normal and stop being vigilant because herd immunity thresholds are being reached. It's not that at all, because you can have a city within a country that it's comfortably above the herd immunity threshold, but actually have a neighboring region that may be actually not being very affected at all, and may be substantially below. So we just have to keep keep being vigilant and apply the policies to some extent according to specific to regions. I'm sure there will be some national policies, but if you see an outbreak starting somewhere, this is probably not saying that you should lock down the entire country again. You should look at that region and maybe lock down for some time that particular region that has not been affected earlier and therefore is being affected now. So it just should be very much local caution. So we also did that we did something similar for heterogeneous connectivity. This is actually the same set of equations, same set of differential equations. Only a force of infection changes, because in the heterogeneous connectivity model, an individual that is more likely to get the infection is also more likely to pass it on to others. So the force of infection needs to account for that, and so we rewrite the force of infection to account for that. But other than that, the results are very similar. The herd immunity thresholds come to values that are very similar to those that we had estimated for the heterogeneous susceptibility model, even though the parameters are not, and coefficient of variation may be quite different, because it's a different model. The heterogeneous connectivity in a way amplifies the importance of heterogeneity, and are not seems to have to be low to be higher when you have heterogeneous connectivity. But then when you have the parameters that are specific to your model estimated, and then you go and calculate herd immunity threshold, that seems to be a kind of a conserved quantity. You just get very similar herd immunity thresholds, even though the parameters have to be readjusted because the model is different. And again, the herd immunity curves are similar to the other to the heterogeneous susceptibility model. Now this is the equivalent for the heterogeneous connectivity. The formula for heritability threshold is only slightly different. There's this factor of 2 that appears here, multiplying this coefficient of variation, and others, and the shapes are very similar. So so this is my last slide.